Hi everyone, this is the instruction that you need for doing the modulus functions unit. So I'm going to get through a lot here in this little video. So here is the syllabus that says investigate graphical, geometric and algebraic properties of absolute value functions in the complex and Cartesian planes. Okay, so we start with a basic definition of modulus and what those signs here actually mean. We've seen them mean different things, but here we're talking about, if we're talking about a number, then if we have a negative value it just makes it positive. Really, that's what the modulus function is. So the modulus of 2 is 2, that's boring. The modulus of negative 2 is 2. So really we're talking about the length, kind of like we were doing with complex numbers where those signs mean the length of the number. Kind of the same idea here, but this is a more mathematical definition. Okay, so we need to first of all be able to draw these things well. So if we look at this little table here, modulus of negative 3 is 3, 2, 1, 0, 1, 2 and 3. So if we go ahead and graph all those points, we get points here, 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 and you'll see what we get when we draw the modulus function is this V-shaped kind of graph that looks like this. Cool. And all modulus functions look like that. Okay, so here's some modulus functions that you should know how to draw them that come from that. Basic transformations. The modulus of x plus 1. So we're just going to do the basic graph and then we're going to move it up 1. So let's do that. That's really simple. There we go there, and that'll be sitting there at 1. Next one here is a transformation, modulus of x minus 1. That is just the same function shifted across to the right 1. And 2 times the modulus of x is just a modulus function, but the gradient is steeper. These ones are a little bit trickier. The modulus of 2x plus 1. When I'm looking at these, I'm thinking, what value of x makes that thing there 0? And the answer is negative 1/2. So I know that this is sitting here at negative 1/2. Because of the 2 in front of the x, it's going to make it steeper. So this is the kind of graph that we're looking at for the modulus function. If we need to know what that y-intercept is, that's easy. If we just replace x equals 0 in there, we get y equals 1. Now really this function here is actually 2 different functions. This branch here is y equals 2x plus 1, and this branch over here is actually y equals negative 2x minus 1, isn't it? Okay, so that helps when you have a modulus function to actually work out what the equation of each branch actually is. Okay, second example, modulus of 2 minus x, same thing. I'm thinking for this one here, what is the value of x that makes that thing there 0? And the answer, of course, is 2. So it's sitting over here at 2, and here it is. Now you might ask yourself the question, is that the same as the modulus of x minus 2? And you would be absolutely right, it is. They're exactly the same graph. For this one here, this branch here is y equals x minus 2, gradient 1, y-intercept of minus 2. We took it back there. And this branch here is y equals negative x plus 2. So hopefully you can see the relationship between those two. Okay, the right hand side is just the negative of the other one. Okay, and the last one here on this page is the modulus of x squared minus 2. Well, that is, the graph of x squared minus 2 would be a parabola. That would do something like this, and it would be sitting down here at minus 2. When we've got the modulus, that just means anything that's negative, or in this case below the axis down here, is just going to be made positive. So what I'm going to do is get rid of this part here, below the axis, and I'm just going to flip it around. So So I'm going to flip it around so it goes like, there we go. Hi everyone, welcome to this second video on modulus graphs. We're going to do some trickier ones now and just kind of look at the more generalities here. Here we've got on the first slide, we've got three different examples to show you what, if you start with a normal graph of sine x, what happens if you go sine modulus of x, or in general, if you have a function that's y equals f of x, then what happens when you do y equals f of modulus of x. So if you have a look at the geometry here, what's happened is really we have just deleted everything to the left hand side of the x-axis there and replaced it with the reflection of everything on the right hand side. That's really what's happened here when we're doing f of modulus of x. For the last one, which in general I could write as y equals the modulus of f of x, then you can see what we have is everything that is below the x-axis has just been reflected in the x-axis, and we saw that in the very last question of the last video. So here's a few graphs, and you could look at them and the question could be, what is the equation of these graphs? So I'll give you a chance to just write down what you think the equation of those two is. Okay, so the first one is just going to be, let's look at this one, y equals, now you can see we've had a transformation, it's shifted 3 across to the left, so I reckon it's just going to be that. And you can check it when you put x equals 0 in there, you get y equals 3 up here, so therefore, yeah, we've got the right y-intercept, so that looks correct. For the one on the bottom, it's looking a lot steeper here. It looks like it's been shifted across a half. So I'm guessing, I guess you could think of it first of all like this. The problem with that is that even though you've got the right, when x equals a half, y equals 0, when you put x equals 0 in there you get y equals a half, which is not what's going on here in this graph. Because of the steepness, I think it'd be better and more correct, and actually correct, to write it like this. So if I just delete that, it would be, let's write that one again. Y equals 2x minus 1. How about that? That looks a lot better. Now when x equals 0, you get y equals the modulus of negative 1, which of course is 1, which is the correct y-intercept sitting right there. Okay, so that's good. Alright, next ones. Here's two more for you to have a go at, so just take a minute to try and do those ones. Right, here's the answers. This one here looks like it's just been shifted across 5. So y is modulus of x minus 5, and the y-intercept is correct, so that looks good. This one here looks a bit steeper than usual. It's at 2, and we're going through 6 over there. Okay, so you could think of it like this. Modulus of x minus 2, but when you put x equals 0 in there, you get y equals 2, not 6. So there's a couple of ways of doing this. I could chuck a 3 at the front there. That would work. And now when x equals 2, we get y equals 0, which is great. And when x equals 0, we get y equals 3 times the modulus of negative 2, 3 times 2, which is 6. So that looks right as well. So you could also probably sometimes see that written like this. And that would also be correct. Okay, trickiest ones here, most important ones here, and these are from the textbook, so you've already got examples of these, but I just wanted to go through them specifically. First one, we want to draw y as a modulus of f of x. Okay, so we need to know that that means that anything below the x-axis is reflected in the x-axis and goes above there. And we can see the answer for that on the next page. In this second example, y equals f, the modulus of x. If you remember back to the first one that we were doing, what that actually meant, it meant that everything to the left-hand side of the y-axis, so all of this part here, just forget about it. Just scrub it out. Forget it even exists, and then we're going to reflect everything on the right-hand side of the y-axis in the y-axis. Okay, so we're going to take this bit here and this bit here, and we're going to reflect it. So you're going to go something like this. So you're going to have an asymptote there, and then you're going to do something like that. Okay, so what we end up with is a mirror image reflection. Okay, you've got to know those two really well. Also take note of the explanation. So take note of that one down there also. Okay, last two, and the trickiest two. The graphs of modulus of y equals f of x and modulus of y equals modulus f of x. Okay, this is really nasty. First one. The way that you do this one is you are going to just leave everything above the x-axis unchanged. So this part here, oops, and this part here, those bits there are going to stay the same. The bit at the bottom you're going to get rid of. Forget about all of that. And what you're going to do instead is just do the reflection of what is above the x-axis. So something that looks like that. So now your x-axis is your mirror line. So sorry about my drawing's not so great, but there you go, something like that. That's what you end up with when you've got modulus of y equals f of x. Okay, last one and most trickiest one is if you've got the modulus on both sides. Here's what to do with those ones. All you do is you draw the original graph, so everything that's there stays, and you've got to add on the reflection of that graph about the x-axis. So what we have stays. We're going to keep that. Was not very good, but let's keep that one there. And this one here. And then we're going to reflect all of that in the x-axis. So if I can have a go at that, it'll be something like this and something like this. So those are very tricky. Rewind them again and have a look at them. They're the trickiest ones for modulus graphs.